Power MOSFET, as I mentioned, is actually coming from the similar devices from information electronics. We have learned MOSFET. Actually, if we talk about FET, field effect transistor, there are two types. One is MOSFET, the other one is junction FET. Junction FET. JFET, in short, JFET. And we know for both JFET and MOSFET, you have N-channel and P-channel. Okay, we learned it before. N-channel and P-channel. That's similar to for power MOSFET. And the power device for ordinary MOSFET is called power MOSFET. The power device for GFET, you can call that power GFET, of course. But usually people call that, they have a special name for that. It's called static induction transistor. So usually for power GFET, they have a special name. We don't get into that detail. Let's look at the structure and symbol. Symbols are the same as in the information electronics. This is the N-channel MOSFET. This is the P-channel MOSFET. Exactly the same as you learned before. Okay. It has 3 terminals also. This is called gate. The 3 terminals for MOSFET. G is gate. Okay, and then you have D, drain. Okay, S, source. Okay, gate, drain, source. These are the 3 terminals for MOSFET. Okay, the structure is also similar. Then again, you can imagine most part is similar to ordinary MOSFET in information electronics, but there must be some differences. Okay, because ordinary MOSFET in information electronics, they cannot handle high voltage and large current. In order to handle high voltage and large current, there must be some differences in the structure. And you can notice that this N- region is the major difference, one of the major differences. For ordinary MOSFET, they don't have this. They don't have this N- region. You just have this N, P, N layer, P layer, and another N layer. But for power MOSFET, you have this extra N- region. And you can again imagine that is for handling high voltage. That makes this MOSFET be able to handle high voltage. Okay? This is also vertical structure, I mentioned. For other fully controllable devices, vertical structure, and this is a multiple parallel cell structure. This is always true. they are similar to GTO and GTR. And especially for MOSFET, this parallel multiple cell, is usually designed as polygon shape. They usually make it as with a polygon shape. Okay. Do we have a picture here? No. You should have some pictures in the English reference book. The operation principle is similar to what you learned before in analog electronics. When you do not apply positive voltage between G and S. Okay, let's see. This is the G, this is the gate. Pay attention to this is the gate. Okay. Between gate, this is the source. Okay. These are the source. Okay. Between gate and the source, when you don't apply positive voltage, then there's no conducting channel. Okay? The current cannot be flowing through because you have this large area, this is an N- area. Okay? And this is a P layer. You see, this is the source, this is the gate. You have N and P, and this this junction here, P-N junction here, is reverse biased. So you cannot have current flowing through. Okay, when you apply positive voltage between gate and source, what happens? The operation principle of MOSFET is like this. When you apply positive voltage between gate, you see this area is gate, this is source. When you apply positive voltage, you are actually, the positive voltage on the gate will attract the electrons, free electrons in this P layer to this region, to be under the gate area. This positive voltage will attract the free electrons in the P region to that area. That will build up what we call a channel, N channel, because you have a lot of free electrons in that area. That's called N channel. And therefore, if you look at this structure, then under this situation you have lower side, this is N material, okay? And the upper side, you have N channel, and through that N channel, you have N material again. So along these parts, everything is N material. Okay? And therefore, you have the current flowing, conducting paths. That is the basic operation principle of MOSFET. Because of the gate voltage applied between gate and source, you are actually establishing this N channel that will be allowing current flow through. Okay? So you can see that that's similar. That's exactly the same as what we learned for analog electronics. The positive gate voltage introduces conducting channel. Okay? And drain current flows through N- region and conducting channel. Okay? That's the operation principle of MOSFET. Then, do you have a question over here? We said this N- region, or N- layer is used to deal with high voltage. So when the device is turned off, is on off state, this is used to block very high voltage because N- means the doping density, the carrier density is very low. Therefore, this semiconductor is almost like intrinsic semiconductor and almost like insulator. Therefore, no current flows through. But the question might be, when this MOSFET is conducting, when you turn on this MOSFET, this N- region, how can this N- region being allowing large current to flow through? This is a very high, low density area. Therefore, how can this large current be flowing through? We know for power diode, okay, for power diode and GTR, we also have similar problem. Okay, you use here you use PIN diode. Okay, here you have also N- region. This I or this N- are used. These layers are used to deal with high voltage. How do you handle when this is conducting? How do you handle this high resistance area? Do you still remember? For power diode, how do we handle that? Conductivity modulation, right. Conductivity modulation. Conductivity modulation. Because for both power diode and GTR, when you are applying positive voltage, that means the p-in junction is under forward direction voltage. Then the N layer will inject a lot of electrons, free electrons, into the N- region, and the P region will inject a lot of free holes into the N- region. Therefore, that makes the carrier density of N- region increasing. When that density increased, you will be allowing higher current. And when you have higher current, then that will be injecting more carriers into N- region. So the conductivity of this N- region will be changed to very high conductivity. That's what we call conductivity modulation. So N- region, when under forward biased voltage, will be changed to have very high conductivity. That's called conductivity modulation. Similar things happen for GTR. If you get into details of operation principle for GTR, that's similar. But for power MOSFET, there's no conductivity modulation. Right? All these, the junction here, no matter in the blocking state or in the conducting state, those p-in junction here, p-in junction between p and n minus, those are all reverse biased. No forward biased p-in junction. So you cannot solve that problem actually. So there is always a conflict for power MOSFET to design the density of n minus region. This n minus region carrier density cannot be too high. If it's too high, then you cannot handle high voltage. And it cannot be too low. If it's too low, then when you are conducting current, then this becomes very high resistance. This is also not good. So there's always conflict for power MOSFET between high voltage capability and large current capability. Okay? Remember this. Okay? That's why in the end we say on page 60, that's usually the voltage of power MOSFET that can the voltage that power MOSFET can handle is usually around 600 volts or less than 600 volts. Okay? You cannot build too high. When you manufacture too high power MOSFET, then the resistance, equivalent resistance of this power MOSFET under on state will be also very high. That's not good. Okay? Let's look at the characteristics. Similar, again, same as what you learned before for information electronics. Again, three areas. And this area is called cutoff region. Again, cutoff region. And then you have this area when you have very low voltage, but the current can be very high. This is for GTR, for transistor, this is called saturation region, but for MOSFET, this is called ohmic region. Ohmic region. Okay, and then this area in between, this is called active region. Active region. That's the same as information electronics. Okay. Switching characteristics. This is a little bit different from GTR. Okay, you can see that in this waveform, the upper side, that's the voltage you generate to apply to the gate, between gate and source. Okay, the second waveform, that's the actual voltage between gate and source. And the third one is the voltage between drain and source, and the current flowing through drain and source. Okay. There is one difference between MOSFET and GTR. We'll talk about that later on. But basically, if you look at this waveform, one thing for MOSFET is similar to GTR. That is, this is a level control. This is a level control device. If you want to turn it on, you always apply gate voltage between gate and source. If you want to turn it off, you remove that voltage. That voltage has to be 0. Or if you want to make sure this MOSFET is turning off quickly, then you have to apply sometimes negative voltage apply negative voltage, and make sure it is turned off. Okay? That's similar. That's level control, similar to GTR. Okay? But if you look at the turning on process and turning off process, there's one thing different. You probably have noticed that. This area. When you turn on the MOSFET and turn off the MOSFET, when you turn on MOSFET and turn off MOSFET, there's always a period of time, very short time, when the voltage between gate and the source will maintain almost constant, no change. And also, during turning off, there's always some time when the gate and the source voltage, that voltage is constant during the turning off. This is what we call, this constant voltage time period is what we call Miller plateau. Did we mention that at the next page? The reason of this constant voltage, the gate source constant voltage period, that interval, that is because of the Miller capacitance. This Miller plateau is really because of the Miller capacitance. Miller capacitance is the capacitance between gate and drain, gate terminal and drain terminal. Why there is capacitance? If you look at the structure, of this MOSFET, okay? Between gate and drain, you have metal here, terminal here, and then you place these metal terminals in parallel. That, of course, will generate capacitance. There's built-in capacitance between each terminals, between gate and drain, between gate and source, between source and drain. Okay. From this structure, you can see there's always capacitance. Okay. Especially the capacitance between drain and gate. This one is called Miller capacitance. When you have this Miller capacitance, let's see, during the turning on process, okay, when you apply positive voltage, the gate voltage will be starting increasing, okay, starting from here. After this gate voltage, GS voltage, has been higher than a threshold voltage, UT. When this is higher than a threshold voltage, UT, the channel in the P layer will be established. Only when this gate voltage is higher than a certain level, that channel will be established. Then you start to have current, because that in channel has been established. The current will be starting to increase. Okay? When this current has increased to the steady state value, there will be a process. After the current has reached a steady state value, there will be a process for the voltage between for the capacitor here. Originally, when this voltage, when this MOSFET is before it's turned on, the voltage between drain and source is upper side positive, lower side negative. Before it's turned on. The capacitor will have upper side positive, lower side negative voltage. So when this current starts to increase, and when the current reaches the steady state level, okay, let's see, the current flowing has reached steady state level, you really need some time for that current to discharge this capacitor, so that the positive charge will be discharged to the ground, so that for the voltage across the capacitor to decrease from very high value to low value. So actual voltage between drain and the source needs to be decreased because of that capacitor. Only when the capacitor charge has been decreased to zero, then the voltage between gate and source will be rising again. Okay? That is Miller capacitance. Because of this Miller capacitance, you can see this plateau. During this, when this Miller capacitance is discharging energy, the voltage of this Miller capacitance is decreasing. At the same time, the voltage between gate and source is maintained almost constant. Okay? That is a very special process for MOSFET. Okay? So if you look at the gate and source voltage in the future, during the lab training, you can take some time, look at the gate and the source voltage for MOSFET. You can notice there is always this Miller plateau there because of Miller capacitance. Okay? Okay? There will be some also discussion in the specifications of power MOSFET. Basically, these are the same as information electronics. There is a definition of rated voltage, rated current. But there's one thing I want to mention. Usually, the selection of power MOSFET is based on the on resistance. This is a very important specification. That is based on resistance. You usually select this on resistance as small as possible. Okay. I will not get into details of those specifications. You read through the textbook after the class. So in summary, if you look at the power MOSFET, you can see power MOSFET is really very good in most of the aspects. Okay? It is a voltage-driven device. Voltage-driven. Okay. This is really different from GTR, GTO, and thyristor. Remember, when we talk about thyristor, GTR, and GTO, we always say we have to inject current to the gate, either positive current or reverse current. So we have to always provide current to control the device. But here, for MOSFET, the gate is insulated, actually. Do you still remember the inner structure of MOSFET? The gate is insulated. Therefore, you cannot inject current. You always apply voltage. Just apply voltage, you can turn the device on or turn it off. So this is much better because you don't have to inject current. So that's voltage-driven device. So the drive circuit is very simple. Okay, that's first advantage. Second, it is a majority carrier device. I'm not sure you still remember this. Majority carrier device. Majority carrier, actually the full name is majority carrier device. MOSFET is a majority carrier device. GTR, transistor, is minority carrier device. Another name for majority carrier device is unipolar. Another name, unipolar device. And then, similarly, minority carrier device. Another name is bipolar device. Okay, so ordinary transistor, GTR, thyristor, GTO, those are all bipolar devices, minority carrier devices. MOSFET is majority carrier device. Why is it called majority carrier? When it's conducting current, the carriers inside the MOSFET, for example, for N-channel MOSFET, the major carriers are always free electrons. Free electrons for N material, for N-type material, that's majority carrier. For N-type material, free electrons is always much higher, with much higher density than holes. So for N material, free electrons is called majority carrier. Holes is called minority carrier. Okay? For P material, the density of holes is much higher than the density of free electrons, right? And therefore, for P material, holes are called majority carriers. Free electrons for P material is called minority carriers. For MOSFET, it is always one kind of carriers carrying currents. For example, for N-channel MOSFET, there's always free electrons. You establish N-channel and free electrons is moving. So that's why it's called majority carrier device or unipolar, because there's only one type of carriers. Okay? And for GTRs, transistors, GTO, thyristors, they have two types. Both electrons and holes are carrying currents. That's why they are called bipolar devices. Okay, I will no longer get into that detail. So, majority carrier devices has good advantages. Okay, The switching, turning on, turning off process will be very fast. Very fast, because you don't need time to inject carriers into N- region. Okay? For GTRs, erasers, or power diode, you need some time to inject carriers into the N- region so that N- region can be very high conductivity to realize modulation conductivity. Therefore, this process for turning on, turning off process for MOSFET is very fast. This process very, very short. But there's also bad thing. The bad thing I already mentioned. There's always conflict. There's always conflict between the ability to handle high voltage and the ability to conduct high current. Because you don't have conductivity modulation here. So that's always the bad thing. Okay, there's one other issue about power MOSFET. It's a body diode. For power MOSFET, there's always a body diode. Or parasitic diode. Parasitic diode. Body diode or parasitic diode for MOSFET. Why? If you look at this structure, you can probably very easily understand that. Look at this structure. Okay, you have M layer, P layer, N- layer, N layer. But if you look at this structure, this actually is also a structure of a PIN diode. Right? You have P layer here, okay, N- layer here, and N layer here. That is exactly PIN structure. That is diode. This diode has the anode terminal of this diode is connected to this P layer. Okay, here. That's A, anode terminal. Okay, this side would be the cathode terminal. So the anode is connecting to the source. Cathode is connecting to the drain. So if you draw equivalent circuit, a MOSFET actually has a diode, parasitic diode, anode terminal connecting to the source, cathode terminal connecting to the drain. So by nature, when you build a power MOSFET, you are actually building also another diode, anti-parallel diode with the MOSFET. Always pay attention to this. For MOSFET, you always have this. When you use power MOSFET, you always pay attention to that. There's always a parallel body diode along with MOSFET. All right. IGBT. That's the last device we want to talk about. This is the combination of MOSFET and GTR. This idea of coming out of a new device is really when people started to look at GTR and MOSFET, power MOSFET. Okay, GTR is good because you have conductivity modulation. Therefore, there's no conflict. I can be able to block very high voltage, but at the same time, because I have conductivity modulation, I can also conduct very high current. For MOSFET, you cannot do that. Okay? But all the other aspects, MOSFET is much better than GTR. Okay? MOSFET is voltage driven. Okay? That's better than GTR. Voltage driven is good because your drive circuit will be very simple. And because you are majority carrier device, so the turning on process and turning off process will be very short. That means you can turn on, turn off very fast. Those are also very good. Okay? So how about, so the idea would be, how can we combine those two devices together so that we keep the good things about power MOSFET and at the same time we also keep good things about GTR. So that's the idea. And that gives us the new device, IGBT. So IGBT, they are much smaller. The on-state losses are much smaller than MOSFET. Again, you have conductivity modulation this for IGBT. But it is easy to drive. If you look at the gate, between gate and source, this is similar to MOSFET. Okay? And this is because it's driving is similar to MOSFET, so the turning off and turning on is similar to MOSFET. But at the same time, it is also similar to GTR because you have conductivity modulation. So you still need some time to inject carriers into N- region and take them out when you will turn it off. So the turn on and turn off process would be between the turning on, turning off speed will be between GTR and MOSFET. So the switching frequency will be higher, faster than GTR, but lower than MOSFET. And when this device come out, it tends to be the best one. It is almost much better than GTO, GTR, those devices. So GTO and GTR became obsolete. They are all replaced by IGBT. Okay? So far this device is widely used between, if you want to use it between 500 volts and 4,500 volts range. The power range would be between several kilowatts to several megawatts. You always select IGBT. Okay? Let's see, how can we do that? The basic difference, the key structure is here. The only difference between this and MOSFET, pay attention to here, is this layer. You are adding another layer here to the MOSFET structure. If you look at the upper side, it is exactly MOSFET. The only difference is that you add another layer here. This is called injecting layer. Injecting layer. Because of this injecting layer, this is the P plus injecting layer. So because of this layer, when you are applying positive voltage, when this device is forward biased, this P layer will be injecting a lot of carriers into the N- region. Therefore, you have conductivity modulation. And therefore, the conductivity of this N- region will become very high. It can be allowing very high current flow through. So that's the only difference. Okay? You can get into details after the class. Okay? The symbol here for IGBT is a combination of MOSFET and GTR. 3 terminals gate, that's similar to MOSFET, but the other 2 terminals is called collector and the emitter. Those are similar to GTR. Okay? And if you draw an equivalent circuit, it can be considered like this. Equivalent circuit of IGBT can be considered as a MOSFET connecting with a GTR. Okay? You do have similar static characteristic. 3 areas again. Cutoff region. And this region for transistor we call that saturation region. For MOSFET we call that ohmic region. But here we took the name of transistor. This is called saturation region. or we just call it on region. This is called off region, that's called on region. Okay? And this area is called active region. That's similar to GTR. Okay? And this turn on and turn off transients, this waveform is similar to MOSFET. You have this Miller plateau here. You see that in the voltage between G and E, gate and emitter voltage. You have that Miller plateau. Here, Miller plateau here. Turning on, turning off, also Miller plateau. That's because the Miller capacitance. Because the IGBT inner structure is similar to MOSFET. So you have this capacitance between gate and collector. Okay? Parasitic thyristor, I don't want to talk about this. This is no longer a problem. The modern IGBTs are no longer having this problem. You can read through the textbook after the class. Specifications, no different, no very special things I want to mention. But there's one thing I want to mention. Remember, for power MOSFET, you always have a body diode. But IGBT does not have a body diode. Okay? But very often, when you buy an IGBT from the market, industry manufacturers of IGBT, they always manufacture one IGBT side by side, they manufacture another diode. Because in the future you will see, when you make a power converter, you always use one fully controlled device with diode. You always have to use diode. So in order to facilitate the usage of IGBT, the companies that are building IGBTs, they also fabricate an anti-parallel fast diode with side by side with a IGBT. Because in the future, when you use power converters, you always use like this. Okay? I will skip the following part because we'll come back later. We'll come back when we finish talking about power converters. I will move to the summary page. Okay, this page. Power electronic devices can be classified into current-driven and voltage-driven, pulse-triggered or level-sensitive, unipolar or bipolar, or composite. We consider IGBT as a combination of unipolar device and bipolar device. Okay? This is the important page I want to show you. So in summary, we have talked about so many devices, but currently there are 4 devices that are very widely used. The others are just disappeared. They are obsolete. Diode, thyristor, power MOSFET, and IGBT. Okay? These are the 4 devices we are still using. You have to always use diodes. You have to use diodes. We'll see that in the following discussion. Thyristor, although it's half-control device, it is still able to handle the highest voltage and largest current. Still has thyristor, although it's half-controlled, not so good, but still has the ability to handle largest current and highest voltage. So in HVDC, high voltage DC transmission system, you still have to use thyristor. Other than that, it is just MOSFET and IGBT. We always use MOSFET and IGBT. For voltage smaller than 500 volts, you use MOSFET. Okay? For voltage higher than 500 volts, then use IGBT. Okay? If you look at the power level, if it's smaller than several kilowatts, you use MOSFET. Higher than several kilowatts, always IGBT. Okay? That's all I want to say right now for power semiconductor devices. From next class, we will start to talk about different power converters. Okay? Again, as I said before, it might be not so interesting in this beginning part. We talk about all different devices. It's always physics, structures. It's not so interesting. And probably it's very difficult for you to understand. A lot of new terminologies, physics, they're not so good to understand. But there's one good thing about this course, that is, when we discuss about power converters, all different power converter circuits, you actually don't have to know very details about semiconductor devices. What you need to do is always consider a power semiconductor device as a switch. You just assume you can turn this switch on and off as you want. Okay? That is the good thing. Okay? After the discussion of about power converter, you can come back, review power devices, and then you have better understanding of this material. Okay? Sorry, I spent 2 more minutes about homework. The Chinese textbook, page 42. Problem number 6, 7, and 8. 6, 7, and 8. This is considered as the second homework. Okay. Our TA will assign you a due time, a deadline for submitting your homework.